7,500 light-years from Earth, hidden in the dust-choked star fields of the constellation Sagittarius, something is winding itself tighter. A spiral of incandescent matter is spinning out from a pair of stars locked in a slow, lethal dance, tracing a perfect logarithmic curve through the void. Astronomers call it a pinwheel. From a certain angle, it looks almost beautiful. It looks like something an artist might paint to represent the heart of a galaxy. It looks like a flower made of fire, but that pinwheel is not a flower. It is a countdown, and the angle from which it looks beautiful is the angle from which it would also kill us. Tonight, we are going to talk about a star you have probably never heard of. A star with a name that sounds like a serial number, because that is what it is. WR104, 3 letters and 3 digits in a catalogue. A speck of light too dim for the unaided eye, drowned out by the dust lanes of the Milky Way's southern reaches. And yet, of all the trillions of stars in our galaxy, this one has been singled out by astronomers, named in scientific papers, debated in conferences, and quietly worried about by some of the most careful minds on Earth. Because WR104 is not just dying, it is preparing to die in a very specific way. A way that involves releasing more energy in 10 seconds than our sun will release across its entire 10 billion-year lifetime. A way that focuses that energy into 2 narrow beams, one shooting out of each pole. And depending on whose measurements you trust, one of those beams may be aimed almost directly at this small blue planet. That is what we are going to explore, not as a horror story, not as a doomsday headline, as something much stranger and much more interesting. The story of how astronomers found a single star, learned to read its rotation from a wisp of dust 7,000 light-years away, and asked a question that no civilization in history has ever been able to ask before. The question is simple. Are we standing in front of a loaded cosmic gun? Before we go any further, if you find yourself drawn to these slow, quiet journeys through the deep cosmos, take a moment to like this video or subscribe to the channel. It is a small gesture, but it is what allows stories like this one to find the people who want to hear them. Now, let us begin. To understand why WR104 has earned its strange reputation, we have to understand what it is, and to understand that, we have to step back and look at how stars die. Most stars do not die violently. Our own sun, a perfectly average yellow dwarf, will swell into a red giant in about 5 billion years, shed its outer layers in a soft cosmic exhalation, and leave behind a slowly cooling ember called a white dwarf. There will be no explosion. There will be no shockwave. The death of the sun, as cosmic events go, will be gentle, but our sun is small. The truly massive stars, the ones born with 8, 20, 50 times the mass of our own, live and die under different laws. They burn faster. They burn hotter. They consume their fuel in cosmic blinks of an eye, and when they reach the end, they do not exhale. They detonate. We call those detonations supernovae, and we have seen them in distant galaxies, brief points of light that, for a few weeks, outshine every other star in their host galaxy combined. WR104 is the kind of star that will end this way. It belongs to a rare and ferocious class of stellar objects known as Wolf-Rayet stars. There are only a few hundred of them known in the entire Milky Way, and each one represents a star that has lived hard and is now in its final act. A Wolf-Rayet star is what happens when a star massive enough to defy the slow death of the sun reaches a stage where it begins to tear itself apart from the inside. Their winds are so powerful that they strip away their own outer atmospheres. They lose mass at rates that defy intuition, shedding the equivalent of an entire Earth every few years into the surrounding void. They are stars that burn so violently they are evaporating themselves as they live. WR104 has a companion. That is the second crucial fact about this system. Locked in orbit with the Wolf-Rayet star is another massive star, an ob-type star, also young, also hot, also producing a powerful stellar wind. Two stars, both screaming radiation and matter into the space between them. And where those two winds collide, in the narrow channel where one stellar storm meets another, something extraordinary happens. The colliding gas is compressed, heated, and shaped into a glowing arc. Then, as the two stars orbit each other every 220 days or so, that arc gets stretched into a spiral, like cotton candy being pulled from a spinning machine. That is the pinwheel. That is the structure that first revealed WR104 to be something stranger and more important than any of the other Wolf-Rayet stars catalogued in the Milky Way. Because here is what the pinwheel told astronomers. A spiral, traced by the orbital motion of two stars, lies in a plane, and that plane is perpendicular to the rotation axis of the system. If you can see the pinwheel clearly from Earth, almost perfectly face-on, like a clock seen from directly above, then you are looking straight down the rotation axis of the entire system. Which means, when the Wolf-Rayet star finally collapses and produces whatever final detonation it produces, you might be standing exactly where its energy is going to be aimed. And we can see the pinwheel of WR104 almost perfectly face-on. That is the discovery. That is the sentence that changed how a certain corner of the astronomical community thought about this one ordinary-looking smudge in Sagittarius. It is not just that WR104 is dying. Many stars are dying. It is that WR104 may be dying in a way that produces a focused, directed, weapons-grade beam of gamma radiation, and the geometry of the system suggests that beam, if it forms, will be pointed at us. Over the next 14 sections, we are going to take that single observation and follow it everywhere it leads. We will look at how astronomers actually measured the angle of a star 7,000 light-years away. We will look at the physics of gamma-ray bursts, the rare and almost inconceivable events that make supernovae look small. We will look at what would actually happen to Earth if such a beam arrived, what would survive, what would not, and what we could possibly do about it. We will look at the recent measurements that have softened the threat and at the lingering uncertainties that have refused to go away. And in the end, we will come back to the deeper question that WR104 forces us to confront. Not whether this particular star will kill us, but whether the universe, beautiful as it appears, has always been quietly aiming weapons in our direction, and we are only now beginning to notice. The story of WR104 does not begin with WR104. It begins in 1867, in a city still recovering from war, in an observatory perched above the rooftops of Paris. Two French astronomers, Charles Wolf and Wolf-Rayet, were working through a survey of bright stars in the northern constellation of Cygnus. They were using a relatively new instrument, the spectroscope, which split starlight into its component colors and revealed, in the dark lines that crossed those rainbows, the chemical fingerprints of the stars themselves. By 1867, astronomers had grown accustomed to what those fingerprints looked like. Most stars, including the Sun, showed dark absorption lines, narrow gaps where specific elements in their cooler outer atmospheres had swallowed light coming up from the hotter interior. It was a quiet, orderly sort of pattern. The kind of pattern that suggested the universe was, on the whole, well-behaved. But three stars in Cygnus refused to behave. When Wolf and Rayet turned their spectroscope on them, they saw something they had never seen before. Instead of dark absorption lines, these stars showed bright, broad emission lines. Light pouring outward at very specific wavelengths, as if the stars themselves were screaming in specific colors. The lines were wide rather than narrow, smeared across the spectrum in a way that suggested the gas producing them was moving at enormous speeds. Something about these stars was profoundly different. They were not merely hot, they were violent. The light they emitted carried, in its very shape, the signature of matter being flung outward at thousands of kilometers per second. Wolf and Rayet published their observations and moved on. They did not know what these stars were. They did not have the physics in 1867 to understand the implications of what they had seen. The idea that stars could lose mass, that they could blow themselves apart from the inside, was not yet part of the astronomical vocabulary, but the name attached itself to the discovery. From that point on, any star showing those broad emission lines, that telltale fingerprint of self-destruction in slow motion, would be called a Wolf-Rayet star. It would take more than a century of astrophysics to understand what was actually happening inside them. And it would take even longer for anyone to realize that one of these objects, lurking in the southern sky, was worth paying very close attention to. WR104 itself was not discovered until much later. Catalogued in the great surveys of the 20th century, it appeared as one of more than 200 known Wolf-Rayet stars in the Milky Way. Nothing about it stood out. It was simply another massive, dying star, embedded in a dusty corner of Sagittarius, far enough away that even powerful telescopes could only resolve it as a single point of light. For decades, it sat in the catalogues without distinction, a serial number, an entry in a database. Astronomers had bigger questions to chase. Why are Wolf-Rayet stars so rare? How do they form? What do they leave behind when they die? WR-104 was just one of many examples to be studied as part of those broader questions, no more interesting than any other. That changed in 1999, when an Australian astronomer named Peter Tuthill turned the world's most powerful telescope on it. Tuthill was working at the Keck Observatory, perched on the dormant volcano of Mauna Kea in Hawaii. The Keck telescopes, twin instruments with mirrors 10 meters across, were among the largest optical telescopes ever built. But even Keck could not, by itself, resolve the fine structure around individual stars at the distances Tuthill was interested in. To do that, he needed a technique called aperture-masking interferometry. The idea was elegant in principle, almost surgical in execution. By placing a metal mask with carefully cut holes over the telescope's primary mirror, Tuthill could turn the single great mirror into something like an array of smaller telescopes, each one viewing the star from a slightly different angle. The light from those different angles could then be combined to reconstruct images at a resolution finer than the telescope alone could achieve. It was a way of squeezing more information out of starlight than the laws of optics seemed to allow. When Tuthill pointed this technique at certain Wolf-Rayet systems, he saw something no one had ever seen before. Around a star known as WR98, he found a dust spiral, a glowing pinwheel of material traced out by the orbital motion of two stars. The discovery was so unprecedented that it took time to convince the astronomical community what they were looking at. Dust around hot stars was supposed to be impossible. Hot stars are violent. Their radiation should shred any dust grain that tried to form in their vicinity. And yet, here was a structure made of dust, glowing in the infrared, spiraling outward from a Wolf-Rayet binary system. Tuthill realized what had to be happening. The two stellar winds, colliding in the gap between the two stars, were compressing the gas to densities high enough for dust to condense in the brief moment before it was blown apart again. The orbital motion of the binary was then sweeping that freshly formed dust into a spiral, like a lawn sprinkler painting a pattern on a summer afternoon. Tuthill turned his attention to other Wolf-Rayet binaries, and one of them was WR104. When the image of WR104 came back, it was, in a quiet way, stunning. A near-perfect logarithmic spiral, cleaner and more symmetrical than the one around WR98. Two complete turns of dust, glowing in the infrared, winding outward from the central binary in a curve so geometrically precise that it could have been drawn by a mathematician. The orbital period was about 220 days. The expansion velocity of the dust was measurable. By tracing the curve outward, astronomers could read the entire history of the system, almost the way a geologist reads layers of rock. Every twist of the spiral was a record of one full orbital revolution, frozen in dust, expanding into space at hundreds of kilometers per second. But there was something else in the image, something that did not become the focus of attention until later. The pinwheel of WR104 was visible in a particular way. It was visible because we were looking at it from above. The spiral lay almost perfectly in the plane of the sky. To see a spiral as a spiral, rather than as a foreshortened ellipse or a thin line, you have to be looking down its axis. A spiral seen edge-on does not look like a spiral. It looks like a smear. The fact that WR104's pinwheel appeared as a clean, open curve meant only one thing. The rotation axis of the entire binary system was pointing almost directly at Earth. That was the moment the question changed. Until then, WR104 had been a beautiful curiosity, a demonstration of how exotic stellar systems could shape the matter around them. After that moment, it became something else, because astronomers already knew by 1999 that when massive rotating stars die, they do not release their final energy uniformly in all directions. They release it along the axis. They release it in beams. And one of those beams, if it ever forms, has our name written on it. For most of the 20th century, astronomers thought they understood how massive stars die. The picture seemed complete. It was elegant. It even had a certain quiet majesty to it. A star many times more massive than the Sun would spend a few million years burning through its hydrogen, then its helium, then a cascade of progressively heavier elements, each fusion stage shorter and more frantic than the one before. Hydrogen burning could last 10 million years. Helium burning perhaps a million. By the time the star was fusing silicon into iron, it had only days left. Iron, sitting at the bottom of the nuclear energy well, cannot be fused to release energy. It can only absorb it. The moment a star's core becomes iron, the furnace goes out. And when the furnace goes out, the star collapses. What happens next in the textbooks of the 1970s and 1980s was the supernova. The outer layers of the star, suddenly with nothing holding them up, fall inward at a quarter the speed of light. They slam into the now collapsed core, which has compressed itself into a neutron star or a black hole in a fraction of a second. The infalling material rebounds. A shock wave races outward through the dying star, depositing such a vast amount of energy into the stellar envelope that the entire outer layer is blown into space. For a few weeks, the explosion outshines the entire galaxy in which it occurs. Heavy elements forged in the dying moments are scattered into the interstellar medium, where they will eventually find their way into new stars, new planets, new biology. This is, in a real sense, where we come from. The calcium in our bones, the iron in our blood, the gold in our wedding rings, all of it was made in the cores of stars that ended their lives this way. And it was, the textbooks said, a more or less spherical event. The supernova radiated its energy outward in all directions. A spherical bomb going off in the dark, lighting up a galaxy. Wherever you stood in the universe, if you were close enough to see it, you would see roughly the same thing. There was no preferred direction, no axis, no beam. The energy went everywhere at once. This picture was supported by decades of observations. Supernovae had been catalogued in distant galaxies since the 1930s. Their light curves rose and fell in characteristic patterns. Their spectra showed the predictable signatures of expanding shells of debris. When one occurred in our own cosmic neighborhood, as supernova 1987, did in the Large Magellanic Cloud, neutrinos arrived at detectors on Earth from all directions consistent with a roughly spherical event. The math worked. The observations worked. There seemed to be very little mystery left. Massive stars died as bombs. The bombs were round. Astronomers had also developed a confident set of rules about which stars would die this way and what the consequences would be for any nearby civilizations. To produce a supernova, you needed a star at least 8 times the mass of the Sun. The closer the supernova, the brighter it would appear, but even a relatively nearby one, say 100 light-years away, would not be considered an existential threat to life on Earth. The radiation pulse would be intense for a brief period. The ozone layer might suffer temporary damage. Animals on the surface might experience increased ultraviolet exposure. There would be ecological consequences, perhaps even minor extinctions among the most sensitive species. But the planet itself would survive. The oceans would not boil. The atmosphere would not be stripped away. Life would continue. The numbers backed up this comforting picture. The closest known Wolf-Rayet star to Earth, IC 2391, sits about 500 light-years away. Betelgeuse, the famous red supergiant in the shoulder of Orion, is roughly 640 light-years from us and likely to explode sometime in the next 100,000 years. Astronomers had calculated, again and again, that even Betelgeuse going supernova would be a spectacular sight in the night sky, but not a danger to the biosphere. It would shine like a second moon for weeks. Its light would cast shadows on the ground at midnight, but the radiation reaching Earth would be insufficient to cause mass extinction. The conventional wisdom, repeated in countless popular articles and astronomy textbooks, was that you needed to be within about 25 light-years of a supernova for it to seriously threaten life on a planet. And there are no stars that massive within 25 light-years of Earth. None. The closest candidates are all hundreds of light-years away. We were, by this reasoning, safe. This was the consensus through the 1970s, the 1980s, into the 1990s. Supernovae were not a real threat. They were a spectacle. Even the most pessimistic scenarios involved gradual, partial damage from a relatively close event, the kind of thing that might stress an ecosystem, but not end it. Astronomers who studied stellar death studied it the way geologists study volcanism, a fundamental process, sometimes dramatic, occasionally relevant to life on Earth in the deep past, in the form of cosmic ray spikes recorded in tree rings or polar ice. But not something to lose sleep over. The cosmic neighborhood was, by stellar standards, quiet. There were no nearby stars massive enough to threaten us, and the stars that were massive enough were all comfortably far away. The galaxy might be a violent place in the abstract, but our particular corner of it was a backwater. Nothing to fear. Then, in the late 1960s, something happened that astronomy did not yet know how to interpret. Satellites built to detect Soviet nuclear tests began registering bursts of gamma radiation coming from somewhere outside Earth. The bursts were brief, lasting from a fraction of a second to a few minutes. They were not from the surface of the Earth. They were not from the Moon. They were coming from deep space, from random directions, with no apparent pattern. American military analysts kept the discovery classified for years, partly because no one was sure what was producing the signals, partly because anything related to gamma-ray detection was considered sensitive. When the data was finally declassified in 1973, civilian astronomers were given a mystery they did not know what to do with. Something out there was producing pulses of the most energetic form of light in the universe. Something was releasing, in brief flashes, more gamma radiation than any known astrophysical source. For 2 decades after the declassification, no one could agree on what the gamma-ray bursts were. Some astronomers thought they were occurring in our own galaxy, perhaps from neutron stars or strange magnetic phenomena. Others suspected they were coming from much farther away, possibly from other galaxies entirely. The distance debate was crucial because the two possibilities differed by a factor of 1,000,000 in implied energy. If the bursts were local, they were unusual but not extreme. If they were cosmological, they were the most violent events in the known universe. The problem was that no one could pin down the locations precisely enough to tell which was true. The bursts were so brief that they were over before optical telescopes could find them. They left no obvious afterglow, no smoking gun, no body. Just a flash of gamma radiation and then silence. It took until 1997 and a fortunate alignment of new satellite technology for the question to be answered definitively. And when the answer came, the entire conventional wisdom about stellar death began to crack. The satellite that broke the gamma-ray burst mystery was called Beppo-SAX. It was an Italian-Dutch collaboration, launched in 1996, and its critical innovation was deceptively simple. Where earlier satellites could detect a burst but could not pinpoint its location with any precision, Beppo-SAX carried instruments capable of doing both at once. When it registered a burst of gamma radiation, it could swing its more sensitive X-ray cameras toward the source within hours. Those X-ray cameras could narrow down the position to a small enough patch of sky that optical telescopes on the ground could then take over and search for any lingering visible light. For the first time, astronomers had a real chance of catching a gamma-ray burst in the act, of following the explosion from its initial gamma flash all the way down through the electromagnetic spectrum, watching it fade in real time across hours and days. On February 28, 1997, that chance came. A burst designated GRB 970,228 lit up Beppo-SAX detectors. The satellite slewed. The X-ray instruments locked on. A faint afterglow was found, and within hours, optical telescopes on the ground had identified a fading point of light at the same position. The astronomers held their breath. They watched the afterglow for days, then weeks, as it dimmed away into nothing. And when it had finally faded enough to see what lay behind it, they found a galaxy. A faint, distant galaxy. The burst had not come from inside the Milky Way. It had come from across the universe, from billions of light years away. The implication was staggering. If the burst was that distant, then the energy it had released in those few seconds was almost beyond comprehension. To appear as bright as it had, from such a vast distance, the source had to be radiating more energy in a brief flash than the Sun would emit across its entire 10 billion year lifetime. More energy in a few seconds than entire galaxies put out in months. The numbers were so extreme that they initially seemed wrong. There was no known process in physics that could account for them. A supernova was bright, yes, but a supernova spread its energy over weeks, and it spread it in all directions. To produce the gamma-ray bursts, you needed something orders of magnitude more violent than a supernova, or you needed to do something to a supernova that concentrated its energy in a very particular way. And concentration was the key. Within a few years of the first afterglow detections, theorists had converged on an answer that resolved the energy problem. The bursts were not isotropic. They were not radiating in all directions. They were beamed. Whatever was producing them was focusing its output into two narrow jets, one shooting out of each pole of the dying object. If you happened to be standing in the path of one of those jets, you saw an inconceivable amount of energy. If you were standing anywhere else, you saw nothing at all. The total energy released was still enormous, but it was no longer beyond the limits of physics. It was just being aimed. This was the moment the conventional picture of stellar death began to fracture. For decades, astronomers had treated supernovae as spherical events. The math had worked. The observations had worked. But now there was a category of stellar explosions that was clearly not spherical. Something was happening when certain massive stars died that channeled their final energy along an axis. Two beams, perfectly opposite, racing outward at nearly the speed of light. Inside those beams, gamma radiation, X-rays, and high-energy particles were compressed to densities and intensities that no spherical explosion could match. Outside those beams, the rest of the universe might never even know the event had occurred. What kind of star could do this? The theoretical work that followed was some of the most ambitious astrophysics of the early 21st century. Researchers built computer models of dying stars, simulating their collapse in 3 dimensions, watching how rotation and magnetic fields shaped the final moments. A pattern emerged. To produce a gamma-ray burst, an ordinary supernova was not enough. You needed something the theorists called a collapsar, a massive star, but not just any massive star. One that was rotating rapidly, one that had shed most of its outer hydrogen envelope, exposing the dense, fast-spinning core beneath. One whose final collapse would form not a neutron star, but a black hole, and whose surrounding material would not fall in cleanly, but would form a swirling disk around the newborn black hole, channeling matter and magnetic field lines into 2 opposing jets that would punch through the star's outer layers and erupt into space. That description, written in the years after Beppo SAX, sounded oddly specific. It sounded like a list of conditions that would be hard to satisfy by chance. Massive star, rapid rotation, stripped envelope, final collapse to a black hole. It sounded, in fact, like a description of a Wolf-Rayet star at the end of its life. This was the moment that the names started to connect. Wolf-Rayet stars are exactly the objects that have stripped away their outer hydrogen envelopes, exposing the fast-burning helium and heavier element cores beneath. They are exactly the kinds of stars whose final collapse, if they are rotating quickly enough, could plausibly form a collapsar. The theorists were not pointing at WR104 in particular. They were pointing at the entire class of objects to which WR104 belonged. Wolf-Rayet stars were no longer just exotic dying giants. They were suspects. They were candidates for the most violent events known in the universe. And one of them, hidden in the southern sky, just happened to be rotating in a way that put Earth at the end of one of its theoretical barrels. There was something else, too. As more bursts were detected and their afterglows tracked, astronomers were able to identify the galaxies they came from. They found, almost without exception, that gamma-ray bursts came from galaxies actively forming massive stars, star-forming regions. Places where the kind of short-lived, high-mass stellar progenitors that the theorists were proposing should actually exist. The bursts were not random. They were correlated with exactly the kind of stars that the collapsar model predicted. The circle was closing. By the early 2000s, when Peter Tuthill's images of the WR104 pinwheel were being studied more carefully, the broader astronomical community had reached a quiet consensus about something profound. Some Wolf-Rayet stars, when they die, would produce gamma-ray bursts. The bursts would be beamed along the rotation axes of the systems. And here was a Wolf-Rayet binary, 7,500 light-years away, whose rotation axis was apparently pointing at us. It was a coincidence that asked to be examined. No one was claiming, in those early years, that WR104 would definitely produce a burst, or that the burst would definitely arrive at Earth, or that even if it did, it would necessarily be catastrophic. The chain of conditional probabilities was long. Each link could fail. But the very fact that the chain existed, that a real star had all the ingredients in roughly the right configuration, was enough to make the question worth asking out loud. The conventional wisdom about safe distances and spherical supernovae had quietly been overturned. The galaxy was not as gentle as it had seemed, and one particular spiral of dust in Sagittarius was suddenly, in a way that no one had quite expected, the most interesting object in the sky. The question that hung over WR104 after the gamma-ray burst connection was, in some ways, the hardest kind of question astronomy ever has to answer. How do you measure the angle of a star? Not its position in the sky, which is easy. Not its distance, which is hard but solvable. The angle of its rotation axis. The tilt of its invisible spin. The orientation of the geometry that, if everything else lined up, would determine whether the next great burst of cosmic violence had your continent's name written on it. 7,500 light-years away. A single point of light, smeared by atmospheric turbulence into a blurry dot in even the best telescopes. How do you read the spin of something you cannot even resolve? The answer was the pinwheel itself. The spiral of dust around WR104 was not just a beautiful curiosity. It was, in effect, a giant cosmic gauge. A protractor written in light, drawn by the orbital motion of the two stars at the center of the system, expanding outward into space at a speed that could be measured and a geometry that could be modeled. If you could see the spiral clearly, you could read the orientation of the binary. And if you could read the orientation of the binary, you could infer the orientation of the rotation axis along which any future gamma-ray burst would be beamed. The pinwheel was, in this sense, the only reason WR104 was discussable as a threat at all. Without it, the system would have been a featureless point of light, and the question of its tilt would have been unanswerable. With it, the question became a problem of geometry. The technique that made the pinwheel visible was the technique that Peter Tuthill had pioneered, aperture-masking interferometry. To understand what this involves, you have to understand the fundamental limit that all telescopes face. Light is a wave. When a wave passes through any opening, it diffracts, spreading out at the edges. The size of the opening determines how sharply the wave can be focused. A small opening produces a wide, blurry image. A large opening produces a sharp one. This is why bigger telescopes see finer detail. The mirror of the Keck telescope, 10 meters across, can in principle resolve details about 10 times finer than a 1-meter telescope. But there is a catch. Earth's atmosphere is constantly churning. Layers of air at different temperatures move past each other, refracting light by tiny amounts in unpredictable directions. By the time starlight has traveled down through the turbulent atmosphere and reached the telescope mirror, it has been smeared. The mirror's enormous resolving power is wasted, blurred away by the air. Astronomers had been fighting this problem for centuries. The most effective solution, in the late 20th century, was adaptive optics, a system of computer-controlled deformable mirrors that flex hundreds of times per second to compensate for the atmospheric distortion in real time. Adaptive optics restored some of the lost resolution, but for the very finest detail, even adaptive optics was not enough. The kind of resolution needed to see structure on the scale of a Wolf-Rayet pinwheel required something more clever. Tuthill's solution was to throw away most of the telescope. Specifically, he placed a metal mask over the Keck mirror with a pattern of small holes cut into it. The holes were positioned so that each pair of them formed a unique baseline, a unique separation distance and orientation. The light from each hole would interfere with the light from every other hole, producing a complex pattern of fringes in the focal plane of the telescope. To the eye, this pattern looked like noise. To a computer running the right mathematics, It was a treasure map. The fringe pattern encoded, in its precise structure, information about the shape of the object the telescope was pointed at. By analyzing the patterns from many short exposures, each one a snapshot taken faster than the atmosphere could blur it, the computer could reconstruct an image of the source at a resolution that the full mirror, blurred by air, could never have achieved on its own. It was as if you had taken a great lens and shattered it into a dozen smaller pieces, and then used the relationships between those pieces, rather than the lens itself, to see. The technique gave up a great deal of light. Most of the photons hitting the mirror were absorbed by the mask, but the photons that did get through carried, in their interference patterns, information that no single large aperture could provide. With this method, Tuthill could resolve features around stars on the scale of a few milliarcseconds. A milliarcsecond is 1,000th of 1/60th of a degree. It is the angular size of a human hair seen from across an ocean. At the distance of WR104, a few milliarcseconds corresponds to a structure the size of our solar system. That was the scale of detail he could see, the orbital separation of the two stars, the first turn of the pinwheel, the way the spiral expanded outward into space. The observations were made in the infrared, at wavelengths longer than visible light. There was a reason for this. Dust glows in the infrared. The newly condensed grains in the pinwheel, heated by the radiation from the central stars, emitted strongly at wavelengths around 2 microns. In the visible, the dust would have been almost invisible, lost in the glare of the binary itself. In the infrared, the central stars dimmed relative to the surrounding dust, and the pinwheel emerged. Tuthill's images, when processed, showed the spiral clearly. 2 complete turns, a logarithmic curve, expanding outward at a precisely measurable rate. That expansion rate was the next piece of the puzzle. By comparing images taken months and years apart, Tuthill and his collaborators could see the dust moving. They could watch the pinwheel rotate. They could measure how fast the spiral was unwinding. The orbital period of the binary turned out to be about 220 days. The dust expansion velocity was several hundred kilometers per second. With those 2 numbers in hand, the geometry of the system could be constrained. The shape of the spiral, when viewed from above, was determined by the ratio of those 2 velocities, the orbital motion and the outflow speed. The shape of the spiral, when viewed from any other angle, would be distorted, foreshortened, compressed. By comparing the observed shape with theoretical models of how the spiral should look from different viewing angles, astronomers could infer the orientation of the system in 3 dimensions. The result was the discovery that made WR104 famous. The pinwheel appeared, to within the uncertainties of the measurement, almost perfectly face-on. The spiral was open, symmetric, undistorted by any obvious foreshortening. The rotation axis of the binary, and by extension the rotation axis of the Wolf-Rayet star itself, was pointed within a small angle of Earth. Early estimates suggested that the axis might be tilted by as little as 0 to 16 degrees from our line of sight. 16 degrees is roughly the angular separation between the 2 pointer stars of the Big Dipper. It is not a lot. That was the geometry. That was what the telescope, the mask, the infrared cameras, and the mathematics had revealed. A dying star in a binary system with its spin axis aimed almost squarely at our planet. Whether that geometry mattered, whether it would translate into actual danger when the star finally collapsed, was a separate question. It depended on physics we were only just beginning to understand, but the angle had been measured. The arrow, if there was an arrow, had been found pointing in our direction. The next question was whether the bow was loaded. The first major discovery, the one that turned WR104 from an interesting binary into a name that began appearing in serious scientific papers, came in 2008. Peter Tuthill, along with a team of collaborators, including astronomers from the University of Sydney and several American institutions, published a paper in the Astrophysical Journal that did something almost no astronomical paper had ever done before. It identified a specific star, by name and catalogue number, as a plausible candidate for a future gamma-ray burst aimed at Earth. The paper was careful. It was hedged with appropriate uncertainties. It did not predict doom. But it laid out, in the clean, dispassionate language of professional astronomy, a chain of reasoning that ended in a sentence no one had expected to read in a peer-reviewed journal. WR-104 might, when it dies, fire a beam of gamma radiation directly at our planet. The reaction within the scientific community was immediate and, in its way, electric. This was not the kind of paper that astronomers were used to. The field had spent decades getting comfortable with the idea that the cosmos, for all its violence, was a safely distant violence. Gamma-ray bursts happened in other galaxies, billions of light years away. Supernovae nearby were rare and not catastrophic. Even the most pessimistic discussions of cosmic threats had treated them as abstractions, as background context for understanding mass extinctions in the deep geological past. Now, suddenly, here was a specific star in our own galaxy with measurements and coordinates and a face on geometry being named as a possible source of exactly the kind of beamed event that the new collapsar models were predicting. It was the first time the abstract had been given a street address. The paper's argument unfolded in stages. First, the geometry. The pinwheel observations, refined and reanalyzed over the years since Tuthill's original 1999 imaging, continued to show the system close to face-on. The new analysis put the most likely inclination of the rotation axis at somewhere between 0 and 16 degrees from our line of sight, with the best fit value sitting around 12 degrees. 16 degrees is the upper bound. Anything within that cone of uncertainty would still mean the system was, broadly speaking, pointed at us. To put the number in perspective, the opening half-angle of a typical long-duration gamma-ray burst jet is thought to be in the range of 5 to 20 degrees. If WR-104's rotation axis was tilted by 12 degrees and its eventual jet had an opening half-angle of, say, 10 degrees, then Earth would be sitting right at the edge of the beam, possibly inside it, possibly just outside. The numbers did not allow a confident answer either way. They allowed only the unsettling observation that we were, statistically speaking, somewhere on the rim of the cone. Second, the physics. The paper laid out, in some detail, why WR-104 was a particularly strong collapsar candidate. The Wolf-Rayet star at the center of the system was estimated to have a mass of around 25 times that of the Sun, possibly more. That put it well above the threshold for eventual core collapse. Its companion, an ob-type star, was also massive, in the range of 10 to 15 solar masses. The two stars were close enough together that their stellar winds were colliding violently, which was visible in the X-ray emission of the system and in the dust formation that produced the pinwheel itself. The binary nature of the system was, in a way, part of what made WR-104 dangerous. Binary interactions can spin stars up. They can transfer angular momentum from orbital motion into stellar rotation, leaving a Wolf-Rayet star at the end of its life, rotating much faster than it would have on its own. And rapid rotation, as the collapsar models had shown, was one of the key ingredients for producing a beamed gamma-ray burst rather than an ordinary spherical supernova. Third, the timing. Wolf-Rayet stars do not live long. The phase that earns them the name lasts only a few 100,000 years, a cosmic eye blink. After that, the star collapses. No one could say exactly when WR-104 would reach the end of its life. The uncertainty range was enormous, anywhere from tomorrow to several 100,000 years from now. But by stellar standards, the end was close. The paper noted that on the timescales relevant to human civilization, even 100,000 years was very recent. On the timescales relevant to biological evolution, it was the day after tomorrow. The combination of these three elements, the geometry, the physics, and the timing, was what made the paper genuinely unusual. It was not the first time someone had suggested that gamma-ray bursts might pose a threat to life on Earth. There have been theoretical discussions for years, calculations of how often a burst pointed at our planet should occur on average, estimates of how much damage one would do. There had even been speculative connections drawn between past gamma-ray bursts and certain mass extinctions in Earth's history. But all of those discussions had been statistical. They had treated the threat as a distribution, a probability spread across all stars and all time. The new paper took the distribution and pulled a single specific source out of it. It named a star. The immediate scientific reaction was not panic. It was, instead, a kind of focused curiosity. Other groups began re-examining the original observations. Independent teams of astronomers checked the inclination measurements, looked for systematic errors, asked whether the face-on geometry was really as secure as it appeared. The pinwheel itself was studied in greater detail, observed at additional wavelengths, modeled with more sophisticated simulations. The general conclusion of these follow-up studies, through the late 2000s and into the early 2010s, was that Tuthill's basic finding held up. The system did appear close to face-on. The rotation axis did appear to point near our line of sight. The geometry was real, even if the precise numbers might be refined. What also emerged from this period of intense scrutiny was a sharper understanding of just how much remained uncertain. The face-on geometry was robust, but the inclination itself was a range, not a point. The collapsar physics was plausible, but it required assumptions about the rotation rate of the Wolf-Rayet star that could not be directly measured. The connection between Wolf-Rayet stars and gamma-ray bursts was supported by circumstantial evidence, but no one had ever caught a burst happening to a known Wolf-Rayet star in real time. There was no direct chain of observation linking the kind of object WR104 was now to the kind of explosion the paper was hypothesizing it might one day produce. The chain of reasoning was strong, but every link carried its own probability of being wrong. This is where the scientific reaction became most interesting, because despite all those uncertainties, the paper did not get dismissed. It got cited. It got discussed at conferences. It got mentioned in popular science articles and television documentaries. It moved into the category of things that astronomers took seriously enough to keep watching, even if they were not yet sure how seriously to worry. WR104 was added to monitoring programs. Its dust spiral was photographed again and again over the years, building up a time-lapse record of the system that allowed for ever more refined measurements of its geometry and dynamics. It became, in a small but significant way, a special star. Not one of the brightest, not one of the most famous, but one of the most carefully watched. One whose every twitch and shimmer was now scrutinized for clues about what it might eventually do. And then, as more data came in, the picture began to get stranger. The strangeness began with the dust. As more years of pinwheel observations accumulated, astronomers gained something they had not had at the start: a time series, a movie. The earliest images from 1998 and 1999, the follow-up observations from 2003 and 2005, the later refinements from 2008 onward, when stacked together in sequence, allowed the team to watch the spiral expand in real time. It was the kind of dataset astronomy almost never has the luxury of producing. Most stellar phenomena unfold over millions of years. Watching one change visibly over the course of a decade is a rare privilege. But the WR104 pinwheel was so fast, so dynamic, that successive observations actually looked different from one another. The spiral grew. New turns of dust appeared at the inner edge. Old turns drifted outward and faded. It was, in the literal sense, a living structure, traced out in real time by the orbital dance of the two stars at its heart. What the time-lapse revealed was a second-order pattern that no one had expected. The expansion of the spiral was not entirely smooth. There were variations. The brightness of the dust changed in ways that could not be explained purely by orbital geometry. Some parts of the spiral were brighter than others. Some seasons of observation showed enhanced dust production. Others showed the structure looking thinner, more delicate, as if the dust factory at the center of the system was working in fits and starts. The orbit of the binary was eccentric, not perfectly circular, and the two stars came closer together at certain phases of their 220-day cycle than at others. At periastron, the moment of closest approach, the colliding stellar winds were compressed more violently. Maury dust formed. The spiral got a little brighter at that point in its history. Months later, when the stars had moved apart again, the dust production slackened. The variations were small but real, a kind of pulse running through the system. a heartbeat readable in the spacing and brightness of the spiral arms. This was, in scientific terms, a gift. It meant that the system was even more constrained than the original measurements had suggested. The variations in dust production over the orbit allowed astronomers to refine their estimates of the orbital parameters. The eccentricity of the orbit, the masses of the two stars, the rate at which the Wolf-Rayet star was losing mass through its stellar wind, all of these could be pinned down with greater precision than before. Each refinement fed back into the central question: what is the geometry of the system, and how confident can we be in the inclination of its rotation axis? For a while in the years following the 2008 paper, the answers kept reinforcing the original picture. Yes, the system was face-on. Yes, the inclination was small. Yes, the axis pointed near Earth. The numbers wobbled within their uncertainties, but the central conclusion held. There was a slight tightening of the error bars, a small refinement here, a reanalysis there, but no fundamental challenge to the framework. WR104 remained, in the public imagination and in the quiet conversations of professional astronomers, the most plausibly dangerous star in the sky. And then came a second discovery that complicated everything. In 2018, a team led by Grant Hill, an astronomer at the Keck Observatory, published a paper that took a completely different approach to measuring the orientation of WR104. Instead of looking at the dust spiral, Hill's team looked at the light of the central binary itself. Specifically, they looked at how the spectra of the two stars changed as they orbited each other. By measuring the precise wavelengths of certain emission lines and tracking how those wavelengths shifted as the stars moved toward and away from us, they could reconstruct the orbital motion directly. They could measure the radial velocities of both components. They could derive, from the Doppler shifts, the inclination of the orbit relative to our line of sight. The result was unexpected. The orbital inclination, as derived from the spectroscopy, was not the small angle that the pinwheel imaging had suggested. It was much larger, closer to 30 or 40 degrees from face-on, perhaps even more. The two measurements were in tension with each other. The dust spiral said one thing, the stellar spectra said another, and the numbers were not subtly different, they were dramatically different. If the spectroscopy was right, then Earth was not sitting near the rotation axis of the system at all. We might be well outside the cone of any future jet. The arrow, if there was still an arrow, might be pointing somewhere else entirely. This was the moment when the WR104 story stopped being a clean narrative and started being a real scientific puzzle. Both sets of observations were good. Both teams were competent. Both used techniques that, in other contexts, had produced reliable answers. And yet they disagreed. Something about the system was not adding up. Either the pinwheel geometry was being misinterpreted, in which case the original inclination estimates were wrong, or the spectroscopic analysis was missing something, in which case the new estimate was wrong. Or, most interestingly of all, both might be partially right, and the rotation axis of the Wolf-Rayet star itself might not be aligned with the orbital plane of the binary. That last possibility, which had been quietly raised in some of the theoretical literature, suddenly took on new weight. Stellar rotation axes do not have to be aligned with orbital planes. In our own solar system, the planets orbit the Sun in a plane that is more or less aligned with the Sun's equator, but not perfectly. Uranus famously has its rotation axis tipped almost 90 degrees from the orbital plane of the planets. In binary star systems, especially binaries that have been gravitationally perturbed by other bodies, by past close encounters, or by mass transfer events earlier in their histories, the spin of one component can easily be misaligned with the orbit. If WR104's orbital plane was tilted 30 or 40 degrees from our line of sight, as the spectroscopy suggested, but the rotation axis of the Wolf-Rayet star itself was tilted differently, perhaps still close to face-on, as the pinwheel had implied, then both measurements could be simultaneously correct. The pinwheel was tracing the orbital geometry. The spectra were measuring the same thing from a different angle. But the actual spin axis of the dying star, the axis along which a future jet would be beamed, could still be pointed near Earth even if the orbital plane was not. What had begun as a clean question, where is the axis pointed, had fractured into something messier. There were now at least two different axes to worry about, and they did not have to agree with each other. The system was showing the kind of complexity that real stars exhibit when you look at them closely. Layers of motion superimposed on each other, orbital tilts, spin tilts, subtle effects of the colliding winds, of the binary's eccentric orbit, of the long history of mass exchange between the two stars. Each new measurement seemed to deepen the picture rather than resolve it. For the moment, the threat assessment did not collapse. The spectroscopic finding made the worst-case scenario less likely, but it did not rule it out. The pinwheel still pointed where it pointed. The face-on appearance of the dust spiral, while now harder to interpret, had not disappeared. WR104 remained, in the quiet vocabulary of the field, a system worth watching. But the certainty of the 2008 paper, the clean narrative of a star aimed at Earth, had given way to something more honest and more interesting, a scientific argument in progress. The arrival of conflicting measurements forced the WR104 community into a deeper kind of analysis. If the orbital inclination and the rotation axis might not be aligned, then it was no longer enough to ask one question about the geometry of the system. There were now several questions, each with its own physics, its own uncertainties, and its own implications for what would actually happen when the star died. Astronomers began assembling a fuller portrait of WR104 as a binary, treating it not as a single dangerous object, but as a complex stellar system with a history. A history written in mass, in motion, in the slow exchange of material between two stars locked in a gravitational embrace for the past several million years. And it was in that history that a pattern began to emerge, a pattern that did not exactly comfort anyone. The pattern had to do with how WR104 had become what it was. Wolf-Rayet stars do not begin their lives as Wolf-Rayet stars. They begin as ordinary massive O-type stars, hot blue giants burning hydrogen in their cores. To become Wolf-Rayet, they have to lose their outer hydrogen envelopes, exposing the helium-rich layers beneath. There are two ways this can happen. The star can blow its envelope away through its own stellar wind, a slow process that takes a few million years and depends sensitively on the star's mass and metallicity. Or, if it has a binary companion, the envelope can be stripped away through mass transfer. The companion's gravity tugs at the outer layers of the larger star, pulling material across the gap between them, accelerating the loss of the envelope, and often spinning up the companion in the process. Binary stripping is faster than wind stripping, and it has a side effect that single-star evolution does not. It transfers angular momentum. It changes how fast the stars are spinning. Growing consensus in the WR104 literature was that binary stripping was almost certainly part of the system's history. The two stars are close together, close enough that mass transfer in the past was likely. The Wolf-Rayet star may have lost a substantial fraction of its original mass, not to its own wind, but to its companion. And in the process, both stars would have had their rotation rates affected. The Wolf-Rayet star may have been spun up, or it may have been spun down. The detailed outcome depends on the geometry of the mass transfer, on the orbital separation at the time, on physics that even sophisticated computer simulations struggle to nail down. What is clear is that the spin of the Wolf-Rayet star today is not a leftover from its birth. It is the product of a complicated past, and it can plausibly be high enough to satisfy the collapsar requirement. This was the third discovery in the chain of revelations that has built up around WR104. Not a single dramatic finding, but a slow recognition that the system had been spun, twisted, and reshaped by its own binary evolution into something whose dying behavior would be difficult to predict from first principles. The Wolf-Rayet star is not a generic dying star. It is a specifically modified one, a star whose rotation and structure have been shaped by hundreds of thousands of years of interaction with its companion. And the kinds of stars that produce gamma-ray bursts in the collapsar model are precisely the kinds of stars that have been modified this way, stripped of their envelopes, spun up by binary interactions, prepared, in effect, for the kind of asymmetric collapse that produces a beam rather than a sphere. There is something almost recursive about this. The same binary configuration that makes WR104 visible to us, that gives us the pinwheel of dust we can image and measure, is also the binary configuration that makes it dangerous. Without the companion star, there would be no colliding winds, no dust spiral, no way to read the geometry of the system from across 7,000 light-years. But also, without the companion star, the Wolf-Rayet star might not be rotating fast enough to produce a collapsar at the end of its life. The very thing that lets us see WR104 clearly is the thing that makes WR104 a plausible threat. The visibility and the danger come from the same source. The companion is both the spotlight and the gun. The implications of this pattern began to ripple outward through the literature. If binary stripping is what creates collapsar progenitors, then the relevant question is not how many massive stars are out there, but how many massive stars in close binary systems are out there. The distinction matters. Roughly 70% of massive stars are thought to be in binary or multiple systems, and a substantial fraction of those binaries are close enough for significant mass transfer to occur over the course of stellar evolution. The pool of potential gamma-ray burst progenitors, in other words, is not small. It is a substantial fraction of the most massive stars in the galaxy, and many of those systems are not visible to us in the same way WR104 is. They do not all produce dust spirals. They do not all have orientations that let us measure their geometry. There may be dozens, hundreds of similar systems in our part of the Milky Way that we cannot easily characterize. WR104 is conspicuous. It is not necessarily exceptional. This realization shifted the framing of the question. It was no longer just about whether one specific star was aimed at us. It was about whether the pool of potentially dangerous stars in our cosmic neighborhood was larger than astronomers had previously assumed. The pinwheel of WR104 had served, in effect, as a discovery vehicle. It had drawn attention to a category of object that might be more populous than it appeared. And the category was uncomfortable because the conditions that produced it, the binary stripping, the rapid rotation, the lost envelope, were not exotic. They were the ordinary outcomes of ordinary stellar evolution in close binary systems, the kind of process that happens routinely in star-forming regions across the galaxy. There was another aspect of the binary history that added to the unease. Mass transfer between the two stars in the long-ago past would have left a record. It would have changed the orbit. Material flowing from one star to the other carries angular momentum with it, and that angular momentum has to go somewhere. Typically, it either tightens the orbit or widens it, depending on the details. The current orbit of WR104, with its 220-day period, is the present-day endpoint of whatever evolutionary process has been operating. Reconstructing that history is hard, but the broad outlines are clear. The system was once different. The stars were once closer or farther apart. The masses were once distributed differently. The Wolf-Rayet star, when it was still a normal massive star, was once larger and more luminous than it is now. The companion was once smaller and may have grown by absorbing material from the primary. All of this happened over a few million years. By human standards, that is unfathomably long. By stellar standards, it is the length of a single chapter in a star's life. WR104 is now in the final chapter. The Wolf-Rayet phase is brief. A few 100,000 years at most, possibly considerably less for a star this massive. The system, in other words, is poised. It has been shaped by its history into a configuration that is now nearing its end, and the end will not be quiet. Whatever the precise geometry, whatever the exact rotation rate, whatever the disagreements between pinwheel imaging and spectroscopic measurement, one thing is not in dispute. WR104 is going to die. It is going to die soon by any cosmic measure, and it is going to die violently. There is a moment in every long scientific story when the questions stop arranging themselves neatly and begin to contradict each other. WR104 reached that moment somewhere in the years after the spectroscopic measurements, and it has not entirely left it since. The cleanest version of the story, the version that fit on a single slide at a conference, was the version from 2008. A face-on pinwheel. A rotation axis aimed at Earth. a Wolf-Rayet star nearing the end of its life, a plausible collapsar in the making. Each element of that story remains broadly defensible, but each element, examined more closely, has developed cracks. And the deepest crack, the one that has refused to close despite years of additional observation, is the question of what is actually inside the system. What kind of object the Wolf-Rayet star really is. Whether it is even the kind of star that will produce a gamma-ray burst at all. The collapsar model, as it has matured over the past 2 decades, has become more demanding rather than less. The original picture, in which any rotating massive star could in principle collapse to form a black hole and launch a jet, has given way to a more restrictive picture. Producing a gamma-ray burst, the modern simulations suggest, requires not just rotation, but a specific combination of rotation, mass, metallicity, and magnetic field structure. The star has to be massive enough to form a black hole at the end of its life. It has to be rotating fast enough that the inner regions of the collapsing core form an accretion disk rather than falling straight in. It has to have a low enough metallicity that its stellar winds have not stripped away too much of its angular momentum before the end. And it has to have a magnetic field configuration that can channel the accretion energy into a tightly collimated jet rather than letting it dissipate in random directions. These conditions are not impossible to satisfy, but they are not automatic either. Most massive star collapses produce ordinary supernovae, not gamma-ray bursts. The bursts are a special outcome, requiring a specific combination of properties that not every collapsing star will have. This is where WR104 becomes genuinely paradoxical. The star has many of the right properties. It is massive. It is in a binary system that has plausibly spun it up. It is in the Wolf-Rayet phase, meaning it has lost its outer hydrogen envelope and exposed the rapidly burning helium and heavier element core. But it also has some properties that work against the collapsar scenario. Its metallicity, for one. WR104 sits in a region of the Milky Way that is relatively metal-rich, meaning the gas from which it formed contained substantial fractions of elements heavier than helium. High metallicity is, in general, bad for producing gamma-ray bursts. Heavier elements increase the opacity of the stellar wind, which makes the wind stronger, which carries away more angular momentum, which slows the star's rotation. The trend in the data, as gamma-ray burst host galaxies have been studied more carefully, is that bursts preferentially occur in low metallicity environments. WR104 is not in a low metallicity environment. It is in the kind of galactic neighborhood where, statistically, bursts are less common. This does not rule WR104 out. Statistical preferences are not absolute laws. A star can produce a burst even in a metal-rich environment if it has been spun up by binary interactions to compensate for the angular momentum lost to its wind. And binary interactions are, as the previous section explored, almost certainly part of WR104's history. The system might be one of the exceptions. It might be a star that has been spun up enough by its companion to overcome the angular momentum drain of its own metal-enriched wind. But it might also not be. The metallicity argument is one of those uncomfortable considerations that has crept into the WR104 discussion over the years, softening the original picture without dismantling it. The star is dangerous if certain conditions hold. Whether those conditions actually hold is no longer something anyone can answer with confidence. The paradox deepens when you consider the alternative outcomes. If WR104 does not produce a gamma-ray burst, what does it produce instead? The likely answer is an ordinary supernova, a bright, brief, more or less spherical explosion. The kind of event that, at a distance of 7,500 light-years, will be spectacular to look at, but not dangerous to life on Earth. A supernova at that distance would, at peak brightness, appear about as bright as a quarter moon. It would be visible during the day. It would cast shadows at night. It would be the most dramatic astronomical event of recorded human history. But the radiation reaching Earth, while elevated, would not be catastrophic. The ozone layer might suffer some damage. Cosmic ray fluxes might increase for a few years. Climate effects, if any, would be modest. Life would continue. The biosphere would notice. but not in any way that would threaten its continuity. The contrast between these two possible outcomes is what makes WR104 such an interesting object to think about. Two stars, dying in similar ways at similar distances, can produce wildly different consequences depending on whether the dying produces a beam. A spherical supernova at 7,500 light-years is a magnificent fireworks display. A beamed gamma-ray burst at the same distance, with Earth in the beam, is something else entirely. The same explosion, the same total energy, but concentrated into a narrow cone instead of distributed across the sky. The difference between a flashlight and a laser. Both can light up a wall. Only one can burn through it. What makes the paradox sharper is that we cannot, from the outside, tell which kind of explosion a given star is going to produce. The properties that determine the outcome, the precise rotation rate at the moment of collapse, the exact magnetic field configuration, the detailed structure of the inner core, are not observable from 7,000 light-years away. We can estimate them. We can model them. We can place statistical bounds on them, but we cannot measure them directly. The actual outcome of WR104's eventual collapse will depend on physics happening on scales of kilometers, deep inside a star, on a timescale of seconds. We are trying to predict that outcome from observations of a dust spiral hundreds of millions of kilometers across, expanding over the course of years. The mismatch in scales is enormous. We are reading the future of an event we cannot resolve from a structure that is, in a sense, the long-ago past of the same system. There is something almost philosophical about this gap. WR104 sits in the catalogue of cosmic threats in a state of genuine indeterminacy. It is not safe. It is not certainly dangerous. It is, in the most literal sense, an object whose future is unknown to physics as we currently practice it. The chain of probabilities that connects the present-day star to a possible catastrophic event on Earth in the future has many links, and the probability at each link is something between 0 and 1. The cumulative probability is hard to estimate. It is small. It is not zero. And it has resisted, in a way that few astronomical questions have resisted, all attempts to make it more precise. This is the unexplainable element. Not unexplainable in the sense of being mystical or beyond science. Unexplainable in the sense that the science itself, honestly applied, returns an answer that is irreducibly uncertain. WR104 might be a future gamma-ray burst aimed at Earth. WR104 might be an ordinary supernova that will give astronomers of some future century the chance of a lifetime. The same star, observed with the same instruments, supports both interpretations. The universe, in this one specific case, has produced an object whose meaning we cannot fully read. To understand why WR104 became, even briefly, the subject of serious scientific worry, you have to understand what a gamma-ray burst actually is, not the polite description that gets used in introductory astronomy texts, the full description. The one that, when you sit with it, makes the rest of the story click into place in a way that no abstract energy figure can. Because the numbers themselves, written on a page, do not communicate what is actually being described. They are too large. They slide off the mind. You have to translate them into something more visceral before they begin to mean anything. Here is the translation. A gamma-ray burst is the brightest electromagnetic event in the known universe. For the brief seconds during which it shines, a single burst outshines all the stars in all the galaxies in the observable cosmos combined. Every star you have ever seen, every star anyone could ever see with any conceivable telescope. 2 trillion galaxies, each containing hundreds of billions of stars, all of them put together, are dimmer than one gamma-ray burst at its peak. That is the energy scale. That is what it means to release more energy in 10 seconds than the sun will release in 10 billion years. The burst is not just bright. It is the upper limit of what the universe knows how to do with light. There is nothing more luminous. There is no physical process more violent. When you stand on a beach and watch the sun set and feel the warmth on your face and understand that you are standing in front of a thermonuclear furnace that has been running for 4.5 billion years, you are looking at an object that, at its absolute peak across its entire history, is dimmer than a gamma-ray burst is in a single heartbeat, and the beam is narrow. That is the part that turns the energy scale from an abstraction into a question of geometry. The jet that emerges from a collapsar is not a sphere. It is a cone. The opening half angle of the cone is somewhere between a few degrees and perhaps 20 degrees, depending on the specific event. Inside that cone, the radiation is so intense that you are essentially looking down the barrel of the most violent natural process in physics. Outside the cone, you might not see the burst at all. The same explosion, viewed from a different angle, produces almost no signal. This is why gamma-ray bursts are detected so rarely despite being so powerful. Most of them are not pointed at us. We see only the small fraction of cosmic explosions whose beams happen, by chance, to be aimed in our direction. For every burst we detect, hundreds more are occurring across the universe at the same moment, invisible to Earth because their jets are pointed elsewhere. The bursts are common. The detections are rare. The geometry filters almost everything out. Now consider what this means for WR104. If WR104 produces a gamma-ray burst, and if the geometry holds, and if Earth happens to be inside the cone, then the radiation reaching our planet would be unlike anything in the recorded history of the biosphere. The gamma rays would arrive at the speed of light, with no warning. There would be no precursor signal. No flash of visible light arriving first to tip off the astronomers. The first sign of the event would be the event itself. Gamma rays slamming into the upper atmosphere on the side of the planet facing the source. The light would be invisible because gamma rays are not visible to the human eye, but the consequences would not be. What happens when a flood of high-energy gamma radiation hits Earth's atmosphere? It does not reach the ground. The atmosphere is thick enough, in terms of column density, to absorb the gamma photons before they can penetrate to the surface. This is the good news, the only good news in this scenario. You would not be standing on a beach and feeling your skin start to burn from the gamma rays directly. The atmosphere would shield the surface, the same way it shields us from the gamma radiation that constantly arrives from cosmic sources at low intensity. But that shielding comes at a cost. The atmosphere absorbs the radiation by interacting with it. The gamma rays slam into nitrogen and oxygen molecules at the top of the stratosphere, depositing their enormous energies into the air, breaking apart molecular bonds, ionizing atoms, producing a cascade of secondary radiation and chemical reactions that propagate down through the atmospheric column. The most consequential of those reactions involves nitrogen. The energy of the gamma rays splits molecular nitrogen, the most abundant gas in the air, into highly reactive nitrogen atoms. Those atoms recombine with oxygen to form nitrogen oxides. Nitrogen oxides are catalysts for ozone destruction. A single nitrogen oxide molecule drifting through the stratosphere can destroy many thousands of ozone molecules before it eventually gets removed from the system. And the gamma ray burst, in those brief seconds, would produce nitrogen oxides on a global scale. Not in one region, not over one continent, across the entire hemisphere facing the source. The stratosphere on that side of the planet would be flooded with ozone-destroying chemistry generated all at once by the energy deposit of the burst itself. The ozone layer in this scenario would not survive. Calculations done for hypothetical nearby gamma-ray bursts suggest that a substantial fraction of the global ozone could be destroyed within weeks, and that the depletion would persist for years. The atmosphere would not return to its pre-burst state quickly. The catalytic nitrogen oxides would continue their work long after the original burst was over, eating away at what remained of the ozone column. With the ozone layer crippled, ultraviolet radiation from the sun would penetrate to the surface in quantities that the biosphere has never experienced. Surface ultraviolet flux would rise by factors of 2, 3, possibly more, depending on the latitude and the season. The light that reaches the ground would be measurably more harmful than it has been at any point in the past several 100 million years. This is the mechanism. Not the gamma rays themselves, killing you where you stand. The damage is indirect. The atmosphere absorbs the burst, but in absorbing it, the atmosphere is wrecked. And then the sun, the same sun that has been benevolent for the entire history of life on the surface, becomes hostile. Its ultraviolet output, normally filtered down to manageable levels by the ozone layer, begins reaching the ground at intensities that proteins and DNA molecules are not adapted to withstand. Phytoplankton in the upper ocean, which produce a substantial fraction of the planet's oxygen and form the base of the marine food chain, will be hit first and hardest. They cannot move out of the sunlight. They float at the surface, where the ultraviolet is most intense, and they are exquisitely sensitive to it. A sustained surge in surface ultraviolet would devastate phytoplankton populations across entire ocean basins. The marine food chain would collapse from the bottom up. Fisheries would fail. The oxygen production capacity of the ocean would decline. The chemistry of the atmosphere itself, on long enough timescales, would begin to shift. On land, the damage would be slower but no less serious. Plants would suffer. Crops would fail or yield poorly. Animals would experience increased rates of skin cancer, eye damage, immune suppression. Humans, with our technological civilization, might be able to protect ourselves and our food sources to some extent, retreating indoors during the worst hours, shielding crops under ultraviolet-resistant materials, accepting reductions in agricultural output, and adapting our diets. But entire ecosystems, which cannot retreat indoors, would unravel. The biosphere has weathered ultraviolet stress before. There is evidence in the geological record of past episodes when the ozone layer was compromised, possibly by past nearby astrophysical events, and the consequences left their marks in the fossil record. A gamma-ray burst from WR104, with Earth inside the beam, would be the most severe such episode in human history. It would not end the biosphere. Life, in its bacterial and microbial forms, would survive. But the complex, fragile, interconnected web of higher life that humans depend on and that we are a part of would be profoundly disrupted. The world that emerged on the other side of such an event would not be the world that existed before it. That is the climax of this story, not the explosion itself, which would last only seconds, but the slow unraveling that would follow. The ozone collapse, the ultraviolet flood, the years of damage rippling through the food chain. The reordering of the biosphere under a sun that has temporarily become an enemy. This is what is at stake in the question of whether one specific star, 7,500 light-years from Earth, is aimed in our direction. The question is not whether the universe is dangerous in general. It is whether this particular sentence of the universe, written across the southern sky in a spiral of glowing dust, ends with our name in it. The implications of the WR104 story for the broader project of understanding stellar death have been quietly significant. The system did not just raise a question about one star. It reshaped how astronomers think about an entire category of objects, and in doing so, it forced a reckoning with assumptions that had gone unexamined for decades. The conventional picture of supernovae as spherical, isotropic, evenly distributed events was not exactly overturned. Spherical supernovae are still real. They still happen. The vast majority of massive star deaths still produce more or less symmetric explosions, scattering their energy in all directions. What changed is the recognition that this is not the only mode. There is another mode, rarer and more focused, in which the dying star channels its final energy along an axis. And the existence of that other mode means that the threat assessment for any individual massive star is no longer a simple function of distance. For most of the 20th century, the safe distance from a supernova was understood to be roughly 25 light-years. Anything farther was background context. Anything closer was a serious concern, but there were no stars that close. The galaxy, by this measure, was reassuringly empty of immediate threats. The WR104 conversation changed that calculus. If a small fraction of massive stars produce beamed events, and if the beams are aimed in essentially random directions, then the safe distance becomes much larger for the stars whose beams happen to be pointed at you. A typical gamma-ray burst, with Earth in the beam, could cause significant atmospheric damage from thousands of light-years away. The relevant volume of space around Earth that needs to be considered when asking about astrophysical risks expands by a factor of millions. The galaxy is suddenly a more populated place, in terms of potential threats, than the older textbooks had suggested. This recognition has reshaped certain corners of paleontology and geology as well. There has long been a category of mass extinction events in Earth's deep past that are not satisfactorily explained by the usual culprits. Asteroid impacts, massive volcanic provinces, sea level changes. Some of the great extinction events of the Phanerozoic eon fit those explanations well. The end Cretaceous extinction, 66 million years ago, has the unmistakable signature of an impact event. The end Permian extinction, 252 million years ago, correlates closely with the eruption of the Siberian traps, but other events are murkier. The Endordovician extinction, around 445 million years ago, killed off a substantial fraction of marine life, including many species of trilobites, brachiopods, and graptolites. Its causes have been debated for decades. Various combinations of climate change, sea level fall, and ocean chemistry shifts have been proposed. None of them have fully satisfied everyone. In the years after the gamma-ray burst connection to massive star death was established, some researchers began to wonder whether a beamed astrophysical event could have contributed to one of these older extinctions. The hypothesis was speculative. It is by its nature hard to test. A gamma-ray burst from 445 million years ago would not have left a direct fossil trace. The gamma rays themselves would have been absorbed by the atmosphere within seconds. What would remain, if anything, would be indirect chemical signatures preserved in sedimentary rocks. Isotopic anomalies, patterns of biological selectivity that match what an ultraviolet flood would predict. Preferential survival of organisms in deeper water where the ultraviolet could not reach. Preferential extinction of shallow water and surface species. The evidence for these patterns at the Endordovician extinction is suggestive but not conclusive. The hypothesis remains on the table as one possible contributor among several. It has not been proven. It has not been ruled out. What the hypothesis represents, even in its unresolved state, is a shift in thinking. The idea that Earth's biological history could have been shaped, at certain moments, by events happening to single stars thousands of light years away is a genuinely new idea. It connects astrophysics to paleontology in a way that earlier generations of scientists did not seriously consider. The biosphere, in this view, is not isolated from the cosmos. It is embedded in a galactic environment whose occasional violence leaves marks in the rock. The marks may be subtle. The connections may be hard to prove, but the possibility exists, and it has changed how some researchers approach the question of why mass extinctions happen. There is another shift, less dramatic but more pervasive, in how astronomers think about stellar death in general. The collapsar model, with its requirement of rapid rotation, low metallicity, and binary stripping, has refined the picture of what makes a star into what kind of explosion. Not every massive star produces the same outcome. The end point depends on properties that vary from star to star. Mass alone is not destiny. Rotation, metallicity, binarity, and magnetic field all play roles. The same initial mass can produce different final products depending on the path the star took to get there. This is a more sophisticated view than the older one. It treats stellar evolution as a contingent process, in which the same starting conditions can lead to different endings, rather than a deterministic one in which mass alone fixes the fate. The consequences of this view extend beyond gamma-ray bursts. It bears on how we understand the production of heavy elements in the universe, on the formation rates of black holes versus neutron stars, on the dynamics of star clusters and galaxies. If a fraction of massive stars die in beamed events rather than spherical ones, then the chemical enrichment of the interstellar medium from those events is also asymmetric. Heavy elements forged in collapsars are ejected preferentially along the jet axes rather than uniformly. Over cosmic time, this affects how galaxies build up their inventories of heavy elements, how planetary systems acquire their starting materials, how the chemistry of the cosmos evolves. The reach of a single recognition that some stars die in beams extends into questions that seem far removed from any individual object. WR104, as a specific star, has played a role in this broader reshaping that is out of proportion to its physical significance. It is one star among many. It is not even the closest Wolf-Rayet star, nor the most luminous, nor the most massive. What made it influential was the combination of factors that drew attention to it. The clean pinwheel that allowed its geometry to be measured. The face-on orientation that made the threat scenario plausible. The publication of the 2008 paper that gave the abstract risk a concrete address. The follow-up observations that complicated the picture without dispelling it. WR104 became, in a way, a teaching object, a case study around which the broader discussion could be organized. Its specific properties matter less than the conversation it enabled. That conversation has produced something that did not exist before. A shared scientific recognition that the galaxy contains a small number of stars whose deaths could matter to Earth, and that identifying which ones, with what degree of confidence, is a legitimate area of inquiry. Whether WR104 itself ever fires its theoretical beam, the framework for thinking about such systems has been built. New candidates are catalogued. New observations refine the population statistics. The risk, even if small, is no longer outside the bounds of scientific discussion. It sits, properly bounded by its uncertainties, on the same intellectual shelf as other low-probability, high-consequence threats. Asteroid impacts, supervolcanic eruptions, solar superflares. The list of things that could plausibly happen to Earth from outside the planet has grown by one category, and the WR104 story is a significant reason it has grown. What this implies, in the longer view, is something modest but real. We have learned to read the sky more carefully. We have learned that certain configurations of stars, certain orientations of dust, certain spectra of light, carry information about potential futures that we could not have extracted a few decades ago. The pinwheel of WR104 is in a literal sense a message, not a message sent by anyone, a message written by orbital mechanics into dust around two dying stars. We learned to read it, and what we read changed, in small but accumulating ways, how we understand the universe we live in. The question that lingers, after all the technical detail has been laid out, is the question of what any of this means for the rest of us. Not for the astronomers who study these systems professionally. Not for the theorists who model collapsing stars in their computers. For the ordinary person going about an ordinary life, who hears that there is a star 7,500 light-years away that might one day fire a beam of gamma radiation at Earth, and is left to wonder what, if anything, to do with that information. The honest answer is that there is nothing to do. There is no precaution to take, no drill to run, no supply to stockpile. The event, if it occurs, will offer no warning. The light from any such burst will arrive at the speed of light, which means it will arrive at the same moment as the news that it is arriving. There will be no announcement, no countdown, no opportunity for human society to brace itself. The first sign of the burst will be the burst itself. And yet the meaninglessness of any practical response does not quite cancel out the meaning of the knowledge. There is something specifically modern about being able to know that a star you cannot see, in a constellation you might not recognize, may have your civilization's fate written into the angle of its rotation. No previous generation of humans has carried that knowledge. The medieval astronomer who looked up at the night sky and saw the bright stars of summer did not know what WR104 was. The 18th century natural philosopher who began to map the Milky Way did not know that Wolf-Rayet stars existed. Even the 20th century astronomer who catalogued WR104 as one entry in a long list of dying giants did not know that the system was face-on to Earth, or that its geometry might matter to anyone but specialists. The knowledge that one specific point of light could, in principle, be a future threat is a product of the past few decades. It is one of the things our species has recently learned about the cosmos we inhabit, and learning it has changed in subtle ways what it means to look up at the sky. The change is not panic. It is something quieter than that. It is the recognition that the night sky, which has always seemed serene, is in fact a place where things are happening. Stars are not eternal. They burn for a while and then they end. Some of them end gently, fading into white dwarfs over billions of years. Some of them end loudly, scattering their substance across light years of space in a few seconds of cosmic violence. The serenity we perceive when we look up is partly an illusion of distance and partly an illusion of timescale. If we could watch the sky in fast forward, compressing 100 million years into a single hour, we would see something very different. Stars flaring and dying, supernovae bursting open and fading away, whole regions of the galaxy lighting up and going dark. The cosmos is not still, it is only slow. WR 104 is one of the places where the slowness has become visible. We have watched the pinwheel rotate. We have measured the spiral expand. We can see, in the time-lapse of observations stretching across 3 decades now, that the system is changing in real time. By the standards of human attention, this is extraordinary. The universe is not supposed to be the kind of thing that changes while you are looking at it. But around WR 104, the universe is doing exactly that. The dust spiral is unwinding. The 2 stars are orbiting. The Wolf-Rayet star is shedding mass into space at a rate that, projected forward, will exhaust its outer layers and trigger the final collapse on some unknown future date. We are watching, in slow motion, the lead-up to an event that may or may not affect us, but that will certainly affect the system itself. There is a way of holding this knowledge that does not require fear. It is the same way of holding any cosmic perspective. We exist in a universe that is mostly indifferent to us, and the indifference is not malicious. WR 104 is not aiming at Earth in any meaningful sense. The star does not know we exist. It does not have intentions. The angle of its rotation axis was set by physics that began before our planet had cooled, and the eventual outcome of its collapse will be determined by processes that have no relationship to the existence of biology anywhere in the universe. If the beam happens to be aimed at us, that is geometry. If the beam happens to miss us, that is also geometry. The star is doing what stars do. The question of whether we happen to be in the path is a question about the configuration of the cosmos, not a question about us. This is, in some ways, the most important thing the WR 104 story has to teach. The universe is not arranged for our benefit, and it is not arranged against us. It is arranged according to its own logic, and we are one of the things that happens within it. Life on Earth has been arranging itself within this cosmic context for nearly 4 billion years. The biosphere has weathered, at various points, asteroid impacts, ice ages, supervolcanic eruptions, oxygen catastrophes, and possibly the occasional astrophysical event whose traces are now too faded to read clearly. Each of those events reshaped what came after. None of them ended the story. Life adjusted. New forms emerged. The biosphere went on. It is reasonable to assume that, even in the worst-case scenarios for WR 104, the same pattern would hold. Life would adjust. The world would be different on the other side of such an event, but the world would still be there. The continuity of life on Earth is not something that one cosmic event, however dramatic, can erase. What such an event could erase is the particular form of civilization that humans have built. The complex web of agriculture, supply chains, energy infrastructure, and ecological services that supports 8 billion people in something resembling modern conditions is a fragile arrangement. It depends on stable climate, predictable seasons, healthy ocean food chains, functional ozone layer. A sustained surge in ultraviolet radiation, persisting for years and disrupting the photosynthetic base of the biosphere, would test that arrangement in ways it has not been tested before. Whether human civilization in its current form would survive such a test is an open question. The species would survive. Pockets of human population would adapt. But the particular configuration of nation-states, global economies, and technological capabilities that defines life in the present moment is not guaranteed to persist through a major astrophysical perturbation. This is the practical content of cosmic perspective. Not that we should be afraid of WR 104 in particular. The probability that the system will produce a burst aimed at us within the next 1,000 years is small. The probability that it will do so within the next century is much smaller still. The chance that any individual person alive today will witness such an event is essentially zero. But the broader point that the WR 104 conversation has surfaced, the point that our civilization is embedded in a galactic environment whose occasional violence has consequences for biology, is real. and it suggests that we should take seriously the project of understanding our cosmic surroundings, mapping the population of nearby threats, learning to read the geometry of distant systems. Not because we can do much about any specific threat in the short term, but because the long arc of survival, for any species capable of looking up and asking these questions, depends on knowing what is out there. We are the first generation in the history of life on Earth that can know. That privilege carries with it a certain quiet responsibility to keep looking, to keep measuring, to keep building the picture of the universe we inhabit, even when the picture occasionally includes things that are unsettling. WR104 is part of the picture. So is the silence in which it sits, slowly winding its spiral of dust across the centuries, indifferent to our attention. What remains unknown about WR104, after all the observations and calculations and refinements, is most of what matters. The system has been studied intensively for more than 2 decades. It has been imaged in the infrared, observed spectroscopically, modeled in computer simulations, written up in dozens of papers. And at the end of all that effort, the questions that would actually allow us to assess the threat with confidence remain mostly open. This is not a failure of astronomy. It is an honest accounting of how much information can be extracted from a point of light 7,500 light years away. The information is finite. The questions are larger than the information. The most basic unanswered question is when will WR104 die? The Wolf-Rayet phase, as the previous sections noted, is brief by stellar standards. A few 100,000 years at most, possibly considerably less for a star this massive. But within that window, the timing is essentially unknown. The star could collapse tomorrow. It could collapse 50,000 years from now. There is no reliable way, from the outside, to determine which point in the Wolf-Rayet phase WR104 has reached. Wolf-Rayet stars do not announce their imminent demise with any obvious signal. They do not pulse, they do not visibly brighten or dim, they do not produce precursor outbursts that warn of the approaching end. They simply burn through their fuel, layer by layer, until the core becomes iron and the collapse begins. From our vantage point, the star looks the same in the year before it dies as it did 100,000 years earlier. The clock is running, but the face is hidden. This temporal uncertainty is consequential for any threat assessment. If WR104 dies tomorrow and the geometry is unfavorable, the consequences for Earth could be serious. If it dies 100,000 years from now, the humans of that distant future may have entirely different capabilities for understanding and responding to such an event. They may have moved to other star systems. They may have developed shielding technologies. They may have evolved into something we would not recognize. Or they may no longer exist at all, having been ended by some other event in the intervening time. The further into the future the collapse occurs, the less it has to do with us specifically. But the timing itself is not something we can predict with any precision. Astronomy can identify a star as being in its final phase. Astronomy cannot tell you which year within that phase the final moment will arrive. The second great unknown is what kind of explosion the collapse will produce. As Section 9 explored, the conditions required for a gamma-ray burst are restrictive. WR104 has some of those conditions. It may not have all of them. The metallicity argument cuts against the burst scenario. The binary stripping argument cuts in favor of it. The actual rotation rate of the Wolf-Rayet star at the moment of collapse, which is the parameter that matters most, cannot be directly measured. Even if it could be measured today, the rotation rate may continue to evolve in the time remaining before the collapse, as the star continues to lose mass and angular momentum through its wind. The endpoint depends on physics happening in the final years and seconds of the star's life, physics that is not accessible to remote observation. We are predicting an outcome from a process whose final stages are hidden from us. The third unknown is the geometry, which the entire WR104 conversation has been built around, and which remains unresolved in the ways Section 7 described. The pinwheel imaging suggests one inclination. The spectroscopy suggests another. The two measurements may both be partially correct, with the orbital plane and the spin axis of the Wolf-Rayet star pointing in different directions. The exact angle between Earth's line of sight and the rotation axis of the dying star, the angle that would determine whether any future jet is aimed at us or not, is known only to within a fairly broad range. The best estimates put the angle somewhere between 0 and 40 degrees, with substantial uncertainty around any specific value within that range. A typical gamma-ray burst jet has an opening half angle of perhaps 5 to 20 degrees. Whether Earth would be inside the cone or outside, it depends sensitively on numbers that are still being argued about in the scientific literature. These three unknowns, the timing, the type of explosion, and the geometry, combine to produce an overall risk estimate that is genuinely difficult to pin down. Different research groups have produced different numbers. Some have argued that the probability of a damaging burst from WR-104 hitting Earth is essentially negligible. Others have argued that it is small but not negligible. Almost no one argues that it is large. The honest answer, in scientific terms, is that the probability is uncertain within a range that includes very small values and somewhat less small values, and that the uncertainty itself is not likely to be reduced quickly. New observations will refine the picture. But the fundamental limits on what can be known about a star 7,500 light-years away in advance of its collapse will not be easily overcome. There are research directions that could narrow the uncertainties. Better measurements of the system's inclination using techniques beyond pinwheel imaging and spectroscopy are ongoing. Polarimetry, the study of how starlight is polarized by its passage through circumstellar material, can provide additional constraints on the geometry of dust structures. Long baseline interferometry, combining the light from multiple telescopes separated by hundreds or thousands of kilometers, can in principle resolve features around stars at angular scales finer than any single telescope can achieve. The Event Horizon Telescope, which famously imaged the supermassive black hole at the center of the galaxy M87, and later imaged Sagittarius A at the center of our own Milky Way, demonstrates what becomes possible when telescopes are linked together across continental distances. Applied to WR-104, similar techniques could potentially resolve the central binary itself, separating the two stars in images for the first time and providing direct measurements of the orbital geometry. Whether such observations will be made, and how soon, depends on observational priorities and the allocation of expensive telescope time. But the technical capability is approaching the level needed. Beyond direct observation, there is also the question of population studies. WR-104 is one Wolf-Rayet binary. The galaxy contains hundreds of others. Most of them have not been studied with anything like the same care. Surveys to identify and characterize the broader population of close massive binaries, particularly those with circumstellar dust structures that allow geometric measurements, are ongoing. As the sample grows, the statistics improve. We will learn what fraction of such systems are face-on to Earth, what fraction are likely to produce gamma-ray bursts at the end of their lives, what the overall rate of beamed events in our cosmic neighborhood is likely to be. WR-104 may turn out to be exceptional, a rare object whose geometry happens to be unfavorable, or it may turn out to be one of many similar systems, with several of them potentially aimed at us at any given moment. The population context is part of what is still being assembled. There is also a longer-term question about whether anything could ever be done to mitigate the risk, even in principle. The honest answer is that no, nothing can be done with any technology that currently exists or that is likely to exist in the foreseeable future. The energies involved are too large. The distances are too vast. The warning time, if any, is too short. A civilization much more advanced than ours might have options. The kinds of options that science fiction sometimes imagines, vast shielding structures, deflection mechanisms, deep underground habitats designed to wait out a year-long ultraviolet flood, are not within reach of current engineering and may never be. The realistic mitigation strategy, if WR-104 turns out to be a serious threat, is the same strategy that has worked for the biosphere through previous catastrophes: survival, adaptation, continuation through the disruption and out the other side. We are not in a position to prevent the event. We are only in a position to know that it might happen and to live in the meantime with the knowledge. There is a particular kind of quiet that settles over a person who has spent enough time thinking about objects like WR104. It is not the quiet of fear. It is not the quiet of resignation either. It is something closer to the quiet that comes from understanding a scale that the mind was not built to hold. The universe is old. The universe is large. The processes that shape it operate on timescales and energies that have no analog in human experience. And we, recent arrivals on the cosmic stage, have somehow developed instruments and mathematics capable of reading those processes from across thousands of light years. We can identify, by name and catalog number, a single dying star in a constellation we cannot see without a telescope, and we can ask whether its rotation axis is pointed at our planet. The fact that we can ask such a question at all is one of the strangest accomplishments of our species. The fact that the answer is not a clear yes or no is a reminder of how much remains beyond our reach. When you stand on a quiet hilltop on a clear night and look up at the sky, you are looking at a small fraction of the Milky Way. The bright stars you can see with your eyes number a few thousand. Almost none of them are individually interesting. They are background, the slow turning of a celestial wheel that humans have been watching for as long as humans have existed. But threaded through that background, invisible to the unaided eye, are the objects that the past century of astronomy has taught us to find. Wolf-Rayet stars shedding their substance into space, neutron stars spinning hundreds of times per second, black holes drawing matter into accretion disks, binary systems whose orbits are decaying through the emission of gravitational waves. The quiet sky above us is not actually quiet. It is full of motion and violence and chemistry, occurring out of sight, at scales that the senses cannot register. WR104 is one of those objects. It is not visible to the eye. It does not appear in any constellation that an ancient sky watcher would have named. The Sagittarius region in which it sits has been called many things by many cultures: the archer drawing his bow, the centaur with his arrow, the dust lanes pointing toward the heart of the galaxy. None of those traditions knew that, embedded in the same field of stars, there was a binary system slowly winding a spiral of glowing dust around itself. None of them could have known. The discovery required instruments that did not exist until recently, techniques that were invented in the past few decades, a kind of attention to specific points of light that no pre-modern astronomy could have sustained. We are the first generation that has ever looked up and seen WR104 as anything other than a faint contribution to the diffuse glow of the Milky Way. There is something to sit with in that thought. The sky has not changed in any way that humans can perceive across the duration of recorded history. The constellations of 3,000 years ago are essentially the same as the constellations of today. The slow proper motions of nearby stars, the gradual drift of the celestial poles due to precession, the occasional appearance of a comet or a nova, these are the only changes that human observers have ever noted with the naked eye. Everything else has appeared fixed, eternal. And yet the universe behind that apparent permanence has been doing what universes do all along. Stars have been forming, burning, and dying. Black holes have been growing. Galaxies have been colliding. The cosmos has been busy in ways that our ancestors could not have detected. Only in the past few generations have we built the tools to see what was always happening. This is the perspective that WR104, in its particular way, helps to illuminate. The question of whether one specific star is aimed at us is small in the grand scheme of things. The probability of a damaging event in any human lifetime is low. The practical consequences for daily life are negligible. But the question opens a larger door. It points at the recognition that we are living in a universe where such questions are answerable in principle, where the geometry of distant systems can be measured, where the eventual fate of individual stars can be predicted within bounds. The universe is not, in this sense, a black box. It is something we have begun to read. The reading is incomplete, and large portions of the text remain in languages we do not yet understand. But we have begun. The other perspective that WR104 invites is the one that runs in the opposite direction. The recognition of how small we are within the system we are reading. The Milky Way contains somewhere between 100 billion and 400 billion stars. The number of Wolf-Rayet binaries within it is on the order of hundreds, possibly thousands. The number of those that are face-on to Earth that could in principle be threats is a small subset of that already small population, and the relevant time scales over which any individual such star might pose a threat are short compared to the age of the galaxy. The cosmos is, on average, indifferent to us. It is not arranged to harm us, and it is not arranged to spare us. The occasional alignment of geometry and timing that could put Earth in the path of a beamed event is a statistical possibility, not a design feature. We are subject to the same statistics that govern every other rocky planet orbiting every other ordinary star. There is nothing special about our exposure, and nothing special about our protection. We are participants in a cosmic process that includes both creation and destruction, and we have no preferential standing within it. There is, perhaps surprisingly, a kind of peace available in this view, not the peace of being safe, the peace of being included. We are not exempt from the cosmic processes that built us. The elements in our bodies were forged in stars that died billions of years before the sun was born. The carbon in our cells, the oxygen in our blood, the calcium in our bones, all of it came from the same kind of stellar deaths that we are now learning to anticipate. We are, in the most literal sense, products of the violence we are now able to study from a distance. The Wolf-Rayet stars and supernovae and gamma-ray bursts that have occurred throughout galactic history did not happen apart from us. They are part of the chain that produced us, and the events that may yet occur will be part of whatever chain extends forward from this moment. We belong to the same universe that may, on some unknown future date, deliver an event that disrupts our biosphere. We do not get to claim the gifts of cosmic chemistry without also acknowledging the risks of cosmic geometry. This is the philosophical content of the WR-104 story. Not that we should fear the sky, not that we should ignore it. That we should understand ourselves as participants in something larger than ourselves, something whose scale and duration we are still learning to perceive. The pinwheel of WR-104 has been winding for thousands of years. It will continue to wind for some unknown time longer. At the center of it, two stars are completing the final chapter of a story that began before our species existed. When the chapter ends, whether it ends quietly or violently, whether the geometry favors us or spares us, the broader story will continue. Other stars will form. Other binaries will spin. Other pinwheels will trace their patterns through interstellar dust. The cosmos will go on doing what the cosmos does. And we, for as long as we exist, will be the part of the cosmos that watches and understands, that reads the patterns and asks the questions, that holds the strange and quiet privilege of being matter that has become aware of its own surroundings. There is a star in the constellation Sagittarius that you will never see. It is too faint, too distant, too obscured by the dust of the galactic plane. If you walked outside tonight and looked toward the southern horizon, in the direction where the heart of the Milky Way pours its diffuse light across the summer sky, you would be looking in the right direction. You would not be able to find it. The star is hidden among hundreds of millions of other points of light, indistinguishable to any human eye, lost in a sea of distant suns. And yet, in that hidden place, something is happening. A spiral of dust is winding outward at hundreds of kilometers per second. Two massive stars are locked in an orbit that brings them closer together every 220 days. One of them is shedding the equivalent of an entire planet's worth of matter into space every few years. The other is being bathed in that flowing material, modified by it, shaped by the long gravitational conversation between them. This is WR-104. 7,500 light years from the cafe where you sit reading these words, older than human civilization, older in its current form than agriculture, older than language. And yet, by the standards of stars, it is young. It has lived for only a few million years. It will live for at most a few 100,000 more. The end is approaching, by cosmic measures, with extraordinary speed. And when it arrives, the energy released in that final moment will be greater than the energy our sun will produce across its entire lifetime. We do not know exactly when this will happen. We do not know exactly what form the explosion will take. We do not know with certainty whether the geometry of the system, the precise angle of the rotation axis of the dying star, will direct the final pulse of energy toward Earth or away from it. What we know is that the question is real. The question can be asked, and asked precisely, in the language of modern astronomy. The answer remains uncertain, but the uncertainty itself is something new in human experience. No previous generation has had the tools to identify, by name, a single distant star and ask whether its eventual death might affect the biosphere of their own world. We are the first. We are the ones who have learned to read the spiral of dust as a kind of geometry written into space, the orbital motion of distant binaries as a kind of measurement of axes we cannot directly see. The reading is imperfect. The interpretation is contested. The conclusions are hedged with probabilities. But the act of reading itself is unprecedented, and it has changed what it means to be the kind of creature that looks up. If you have stayed with this story through all of its sections, you have followed a thread that begins in 1867 in a Paris observatory and ends, for the moment, with the unresolved question of where a single star is pointing. Along the way, the thread has wound through the discovery of Wolf-Rayet stars, the development of aperture-masking interferometry, the unraveling of the gamma-ray burst mystery, the collapsar model of stellar death, the spectroscopic measurements that complicated the original picture, the deep uncertainties about timing and geometry, and the type of explosion to come. The thread is long. It has many turns, and at the end of it, the central question remains open. We do not know whether WR-104 will kill us. We do not know whether it will fire its theoretical beam in our direction. We do not know whether it will produce a beam at all. What we know is that the question has been asked, and that the asking matters, even when the answering does not yet arrive. There is, finally, a way of holding this story that does not depend on its resolution. Whether or not WR-104 ever fires its beam at Earth, the system itself is real. The two stars are real. The spiral of dust is real. The death that is approaching, on whatever timeline, is real. And the fact that we know any of this, that we can sit in a quiet room and read about the orientation of a binary system 7,500 light years away and understand what the words mean, is a fact about our species that is worth pausing over. We have built, in the past century, an extraordinary capacity to perceive the universe we live in. The perception is incomplete and frequently humbling, but it is genuine. We are not blind to our cosmic surroundings. We have begun to see. The pinwheel of WR-104 will continue to turn. The two stars at its center will continue their long orbit. At some point, in some year that no one can name, the Wolf-Rayet star will exhaust the last of its fuel. The core will collapse. What follows will be one of the most violent events the local region of the galaxy has produced in a long time. The light from that event, whether beamed or spherical, will begin its journey toward Earth. It will travel for 7,500 years, crossing the distance between Sagittarius and our solar system. And then it will arrive. Some future generation, our descendants or whatever comes after them, will see what we have only modeled. They will know the answer to the question we are currently asking. They will know whether the geometry was favorable or not, whether the beam was real or imagined, whether the consequences were severe or mild or nothing at all. We will not be there. The question we have spent these hours considering is not a question for us. It is a question for them. What we have is the question itself. The strange privilege of living in the time when the question first became askable, of being among the generations that built the instruments and developed the theories and assembled the data that allowed the question to be posed. The answer will belong to someone else. The asking belongs to us. That is, in its own way, a kind of inheritance, a kind of responsibility. We are passing forward to the future the knowledge of what is out there, what to watch, what to keep measuring, what to keep refining. The next generation of astronomers will know more than we do. The generation after that will know more still. And somewhere in that long forward chain, possibly in the distant future, the answer will come. Until then, the pinwheel keeps turning. The stars keep orbiting. The dust keeps spiraling outward into the dark. And we keep looking up, on clear nights, toward a constellation we can see and a star we cannot, wondering what the universe is preparing for us and how much we will ever know before the answer arrives. If this journey through the strange and unsettling story of WR104 stayed with you, if it left you looking at the night sky differently than you did when you began, take a moment to like this video. Subscribe to the channel if you would like to follow more of these slow, quiet explorations into the deeper corners of the cosmos. Share it with someone who would appreciate the kind of question that takes a few hours to ask properly. And in the comments below, tell us where you are watching from, what country, what city, what hilltop or apartment window. The universe is large. The questions it raises are larger. But the conversation about them happens here, among the small community of people who still take the time to look up and wonder. Thank you for being part of it.